some force field, big F. Now, apply Newton's second law, that the force at any point on the curve is going to be equal to m, the mass of the object, times r double prime of t, which is the acceleration. A of t, which is also the derivative of velocity, v prime of t, which we'll also use. So this is just F equals ma happening here. Okay. Now, so now we use this in order to evaluate the line integral. And we're not saying at this point that big F is conservative, but we'll work that in later. So now if we evaluate the line integral in this manner, in a direct way, then what we get is integral from a to b. And now this, F evaluated r is going to be the mass times the acceleration. And then we take the dot product with r prime, which happens to be the velocity. Okay. Now, it turns out that this is something that we can evaluate. Now, m is a constant, we're assuming here, so we'll just pull that out. Now to see what this is the integral of, I'm going to specialize to the one variable case. So if you have any function y, and you're looking at y prime times y double prime, and you want to anti-differentiate that, all right, we'll assume we're functions of x. This is something that we can actually figure out, regardless of what y is. So we have y prime times y double prime. We can actually figure out what this is. Now, if you're not sure how, let's think of a similar case, y times y prime. What is the antiderivative of that expression?
Y squared plus c.
Almost.
Y squared divided by 2.
Yes, yes. So this is 1/2 y squared. Yes, plus c. All right, so therefore, what must this be? Yeah, 1/2 y prime squared. All right, so now we'll work that into here. Here we have a dot product, but the idea applies, the same idea applies because we're looking at a second derivative multiplied by a first derivative for each component, and then we're adding it up. So instead of something squared, because we're dealing with a vector quantity here, we're going to have 1/2 m, integral from a to b, times the derivative with respect to t of r prime dot product with itself. So that's the way it works out in this vector case. And by looking at individual components of these vectors, you can see how this idea applies. But think back to last semester, or whenever you took Calc 3. What is the dot product of a vector with itself? Geometrically.
The magnitude.
Yes, the magnitude. Not exactly magnitude, but what of the
Like a unit this?
no. It's not exactly the magnitude by itself, but what?
Magnitude in its direction.
No. Magnitude squared. All right. All right, so I'll just fill in this magnitude of a velocity squared. Alright, but we're integrating this derivative, so we're just going to get 1/2 mass magnitude of velocity evaluated at B squared minus 1/2 velocity of A squared. What's 1/2 mv squared? What's you physics people?
Kind of sounds like
Kinetic energy. So in other words, I can write this as K of B minus K of A. So it's the kinetic energy at this point minus the kinetic energy at that point. And this is, now the line integral, that's for work. So the total work done is equal to the change in kinetic energy from point A to point B. All right. Okay, now let's assume that big F is also conservative. We did not use the assumption of conservativeness here, but now we are going to throw it in. Okay, we don't need this anymore. So then big F is gradient of some function little f. It's also the gradient of, or minus the gradient of this function capital P, which is a potential energy. Of the object at any given point. All right. So, because the function little f is actually called a potential function for big F. So here we have force being equal to minus the gradient of potential energy. So now let's evaluate this line integral again. Only now we're going to use this. So it's minus gradient of P. So now we can apply the fundamental theorem of line integrals, and we get capital P at the endpoint, or minus, can't forget the minus, plus P at the initial point A. And this is also equal to the work, because the line integral is always equal to the work no matter how we end up interpreting this vector field. So we have two different representations of a work. It's either the change in kinetic energy, or it's minus the change in potential energy. So since they're both equal to the work, let's set them equal to each other. So now we have kinetic at B minus kinetic at A is equal to minus potential at B plus potential of A. Let's rearrange.
Is it safe to say the work is negative from A to B done on the object?
Well, it all depends on the vector field. So if I rearrange, I get the kinetic at B plus the potential at B is equal to the kinetic at A plus the potential at A. So the total energy, kinetic plus potential, is the same at both points. So we have this is conservation of energy. And this is actually why the term conservative is used to describe a vector field that is the gradient of a potential function. So when an object is moved along a curved path under the influence of a conservative force field, then the total energy, kinetic plus potential, remains constant. Right? So that's the law of conservation of energy.
But, and over here, where did the DDT come from?
Oh, because what I'm doing is I'm saying that this part right here is the derivative